lecture in module 7 on finite element method. We had finished with the introduction and weighted residual formulation. In the second lecture we also had a look at variational formulation and we looked at some shape functions. In this lecture we are going to continue with shape functions and numerical integration, and then we would follow up with FEM application to scalar transport. So let us have a brief recap of what we did in the previous lecture. We had briefly discussed variational formulation, and then we had started off discussing different types of shape functions used in finite element analysis. We discussed one-dimensional elements. We also discussed few two-dimensional elements with rectangular elements. Now in this lecture, which is third lecture in this series, we are going to discuss further few more shape functions and the numerical integration which we require in finite element analysis. So we will continue with the shape functions. In two-dimensional elements we will take up a look at triangular elements, and then we will also have a look at few three-dimensional elements, and then we will define what we mean by isoparametric elements, which are very commonly used in curvilinear domains, and then we will have a look at how do we evaluate the integrals which cannot be evaluated analytically. So we will look at two approaches, one the Gaussian quadrature, which is used for the integration of line elements or brick elements, and then we will have a look at the integration procedure for triangle or tetrahedral elements. So we were discussing the standard shape functions for two-dimensional elements. We covered rectangular elements. Now we will start off with triangular elements. We will first define what we mean by natural area coordinates for a triangular element, and in terms of this natural area coordinates we will define the shape functions for linear and quadratic elements. So let us first have a look at what we mean by that area coordinates for a triangular element. So let us draw up a triangle in xy plane. So why we need this area coordinates for a simple reason that though we can write our shape functions in terms of x and y, the expression is a bit more complicated. The integration is also a bit more involved, but if we convert it into what we call a natural coordinate for triangular elements, similar to what we had in the case of rectangular elements, the life becomes a lot easier. So let us draw a triangle. So a typical triangular element. Let's number our nodes as this is node 1, or this is rather the vertices of the triangle. Let us number them as 1, 2 and 3, and let us consider an arbitrary point P which is inside this triangular elements. Now we can have two sets of coordinates. So in our xy coordinate P would be given by, let us say, Pxy. Now we would define area coordinates which we are going to call area coordinates. We would use symbol L1, L2 and L3. We will define what do we mean by these three. So in terms of these area coordinates, point P can also be represented as L1, L2 and L3. Now you might be surprised here that in the Cartesian reference frame P is represented only by two numbers. Here we need three numbers, and we would see these three numbers are not independent. There are only two independent numbers here. Now let us join this point P with three vertices. So thereby we effectively divide our triangle into three subtriangles. The subtriangle which is straight in front of the node 1, this area would be called A subscript 1. Okay. So, this is the one which lies in front of the node 1, or rather we can say that the base of this triangle is the side which is opposite to our vertex 1. Similarly, the triangle whose base is opposite to vertex 2, area of that we will denote by A2, and the area of the triangle which is opposite to vertex 3, we will denote it by A3. Now, let area of the triangle be A of the triangle, let us call it 1, 2, 3, be capital A. So, we can clearly say this A1 plus A2 plus A3 is equal to A. Let us call this as equation 1. Now, how do we define our area coordinates? So, this area coordinates are defined as the coordinate L1 is area A1 divided by A, coordinate L2 is area A2 divided by A, coordinate L3 is A3 divided by A. So, let us call this as equation 2. So, now from 1 and 2 it is obvious. So, thus what we have at L1 plus L2 plus L3, that is equal to A1 plus A2 plus A3 by A, that is equal to 1. So, what we say that these three coordinates are interrelated. So, we have got only two independent coordinates. If we know L1 and L2, we can find out what the values of the third coordinate is. So, in a sense we have got two independent numbers to represent the coordinates of a given point P in our triangular element. Now, using these definitions, we can clearly put the coordinates of three vertices which are defined. For vertex 1 is L1 coordinate would be 1, because when P lies at 1, A1 is whole of the triangle, L2 coordinate of 1 is 0, and similarly its L3 coordinate is also equal to 0. When we come to point 2, if P is constant with the vertex 2, A2 is whole of the triangle area. So, we will have L2 is equal to 1 at vertex 2, L1 is equal to 0 and L3 is equal to 0. Similarly, at vertex 3 we have got L1 is equal to 0, L2 is equal to 0 and L3 is equal to 1. Some more things which you can observe, that along line 2, 3, if P lies at the side 2, 3, what will happen, that A1 would be 0. So, that L1 coordinate along this line would be 0 and L2 and L3 they will range in the range 0 to 1. Same holds good with between 1 and 3, that is along the side 1, 3, L2 coordinate would be 0 for all the points. So, this line 1, 3 it represents basically L2 is equal to 0 line, line 1, 2 it represents L3 is equal to 0 line, and the side 3, 2 represents L1 is equal to 0 line. So, this is our definition of the area coordinates. Next we would be interested in finding out what is the relation between these area coordinates and xy coordinates. So, to find out the relationship between xy and this L1, L2 and L3. The coordinate of any point, xy coordinate of any point, that can be represented in terms of these natural coordinates. So, what we will have is at x coordinate of a point P would be given by L1 x1 plus L2 x2 plus L3 x3. Similarly, y coordinate is given by L1 y1 plus L2 y2 plus L3 y3. Okay, now we can collect these equations together. The equations 3, 4 and 5, they can be written together in a matrix form. So, if you write them in matrix form, equation 3 can be written as the product of a matrix with these coordinates L1, L2, L3, and then the right hand side we are going to put as for equation 3 the RHS was 1. From equations 4 and 5 we would take the left hand side things which is our x and y, because the terms involving the natural coordinates we are going to now put in the left hand side. So, first row is basically 1 1 1, that is multiplied by this vector L1 L2 L3, that should give us 1. So, L1 plus L2 plus L3 is equal to 1. So, this is our first line represents equation 3. The second one we will put x coordinates x1 x2 x3. So, that x1 L1 plus x2 L3 plus so L2 plus x3 L3, that would become our x coordinate, and then y1 y2 y3 in the third row. So, that y1 L1 plus y2 L2 plus y3 L3, that gives us our y coordinate. So, now we have got a system of equations which relate L1, L2, L3 and xy coordinates. So, now we can solve this system of equations. So, solve the system of equations to get L1, L2 and L3 in terms of the Cartesian coordinates. Cartesian coordinates x, y, and if you do that, what we will see that we can write in a shorthand notation. Let us call it L alpha. This can be written as A alpha plus B alpha x plus C alpha y divided by 2 times that area of the triangle. Okay. And we can clearly see that how do we define the area of a triangle. Area of the triangle is basically half of this determinant 1 1 1 x1 x2 x3 y1 y2 y3. Okay. In expanded form, we can substitute here now. This alpha will take the values 1, 2 and 3. In fact, we need to compute only 2 of them. The third one is obtained by the relationship L1 plus L2 plus L3 is equal to 1. So, here using Cramer's rule, you can easily see that this A1, if alpha is equal to 1, A1 is x2 y3 minus x3 y2, B1 is y2 minus y3, and C1 is x3 minus x2. Similarly, for the second coordinate, when alpha is equal to 2, we get A2 is equal to x3 y1 minus x1 y3, B1 is y3 minus y1, and C1 is x1 minus x3, A3 is x1 y2 minus x2 y1, B3 is y1 minus y2, and C3 is y2 minus y1. So, we can use these values to find out what are the natural coordinates L1, L2 and L3 of a point if we know its Cartesian coordinates. Now, in terms of these, it is very easy for us to define now the shape functions of the triangular elements. So, now let us take first scenario, is what we call 3 node, or we also call it linear element. Okay, so, this is the most basic 2D element. So, in this case, our nodes are the 3 vertices of the triangle 1, 2 and 3, and the shape functions are for the linear elements N1 is equal to L1, N2 is equal to L2 and N3 is equal to L3. So, now you can easily see the simplicity which has been introduced by the use of area coordinates, that our shape functions are expressed in a very simple form. And you can also see this is an isoparametric element which we will introduce here, like just for the sake of revision. Please note down that this x coordinate is again given by this sigma n I x I is equal to 1 to 3, L1 x1 plus L2 x2 plus L3 x3, and similarly y coordinate I is equal to 1 to 3 n I y I. So, since n i's they get the values of L i's, so we have L1 y1 plus L2 y2 plus L3 y3. So, in effect our basic this linear triangular element is an isoparametric element. Let us have a look at one more triangular element. Let us take a triangular element for which the shape functions are of second order, that is we will call it as a quadratic and in this case we will have 6 nodes. So, let us have a geometric representation of this quadratic element, and the numbering convention which is commonly employed 1, 2 and 3, these are 3 primary nodes. Mid-sized nodes are numbered again in similar order, that is the mid point of 1 and 2, that would be numbered as node 4, the same cyclic order. The midpoint of 2, 3, that would be called node 5, and midpoint of 1 and 3, that would be called node 6. So, remember these 4, 5 and 6, they are midpoints of the respective sides. So, in terms of area coordinates, what let us note down coordinate of each of these nodes. So, node 1 will have the coordinates 1, 0, 0, node 2 has got coordinates 0, 1, 0, node 3 has got coordinates 0, 0, 1, node 4 it is midway between 1 and 2. So, L1 is half, L2 will also be half, and L3 coordinate is 0 along this line. Node 5 L1 coordinate is 0, L2, L3 they both have value equal to half. Now, node 6 this is half, 0, half. So, now how do we define the shape functions? So, the shape functions for this quadratic element are, we will first define the shape functions for corner nodes. So, that is case A. Shape functions for corner nodes, that is nodes 1, 2 and 3. We will write in a fairly compact form, n alpha is given by 2 L alpha minus 1 times L alpha. So, alpha takes the values 1, 2 or 3, or if you want to demystify it, write in expanded form, let us write for each node separately. So, your shape functions n1 would be twice of L1 minus 1 times L1, n2 is given as 2 L2 minus 1 time L2, and n3 is equal to 2 L3 minus 1 times L3. Now, can we verify whether these satisfy the requirements which we had mandated for each shape function? So, before we do that, let us write the shape functions for the remaining 3 nodes, that is midpoint nodes. So, shape functions for midpoint nodes n4 is given as 4 of L1 L2, n5 4 times L2 L3, and n6 is 4 times L3, L1. It is very easy to verify these things, because at node 4 for instance n4 must be equal to 1, and since coordinates are 1 by 2, 1 by 2, their product of L1, L2 is 1 by 4, so this must be multiplied by 4 and so on. So, now we can verify the two properties which each shape functions should satisfy. So, verification. Let us first verify the reverse order. First let us say Kronecker delta property. For the nodes for 4 and 5, this n4, n5 and n6 is straightforward, that the values of two coordinates which are involved in the definition, they are 1 by 2 each. So, multiply by 4, that easily gives us a value of 1, and definitely their value elsewhere is 0 at all other nodes. The value of these n4 for instance, if we find out its value at node 3 or node 1, it will become 0. So, this Kronecker delta property is very easy to verify. We can also verify this property for, let us say, let us do for one n1. So, n1 at node 1, this is equal to 2 into 1 minus 1 to 1, this is definitely 1. And how about n1 at node 2? At node 2 the coordinate L1 is 0, so it becomes identically 0. At node 4, n1 at 4, that will be 2 into half minus 1 into half, so that is again 0. So, we can verify it for each node. So, all the shape functions do satisfy Kronecker delta property. Next, the partition of unity. For that we need to find out whether their summation of all these shape functions n I is equal to 1 to 6, that is what we need to find out. So, now let us do that. Let us write each one in expanded form. So, n1 becomes 2 L1 square minus L1, L2 would become 2 L2 square minus L2, n3 is 2 L3 square minus L3 plus 4 L1 L2 plus 4 L2 L3 plus 4 L3 L1. So, this we can write as twice of L1 plus L2 plus L3 whole square minus L1 plus L2 plus L3, and we know this L1 plus L2 plus L3 is equal to 1. So, we have got 2 into 1 square minus 1, which is equal to 1. So, these shape functions do satisfy the partition of unity. So, there is absolutely no problem with the satisfaction of two primary conditions which these shape functions must satisfy. Okay. Next, let us move on to 3 dimensions. So, in 3 dimensions we will have a look at what we call rectangular prism elements. We have got variety of options. We can have rectangular prism elements, and we can have triangular prism elements. We can have tetrahedron elements. We can have what we call wedge elements. There are a variety of options available. We will have a look at two of the basics ones. Basically, we would have a look at rectangular prism elements, and we will have both the types, Lagrange family and serendipity family. Tetrahedral elements are very similar to our triangular elements, and we have to introduce what we call volume coordinates in place of area coordinates to define these tetrahedral elements. Now, please remember that both of these types, that is rectangular prism elements and tetrahedral prism elements, are the ones which are most widely used in finite element analysis. So, now let us have a bit detailed look at our 3D rectangular elements. As usual, we can have two sets here. The first one we are going to look at is what we call Lagrange family. And for the Lagrange family of elements, the shape function can be written as the shape functions for element of any order, that is whether we are dealing with linear elements, quadratic elements or cubic elements and so on, can be expressed as products of 1D Lagrange polynomials. That is, if you want to write a generic shape function n alpha for a node alpha, this can be expressed in terms of what we call n capital I, n capital J, n capital K. Now, I, J and K, they are being used to represent one dimensional Lagrangian shape functions in x, y and z directions respectively. So, if you use the symbol for Lagrangian polynomials, we can write this as L of I x I n L j eta n and L k zeta p, where n, m and p denote the number of subdivisions along each side. That is how many number of subdivisions for this element we have got along x direction, y direction and z direction for such an element. And the definitions of natural coordinates of coordinates xi, eta and zeta is very similar to what we did for the two dimensional case, that is our xi is defined as x minus xc divided by L of x so yc L of y. Okay. Now, Lagrangian 3D rectangular elements, they will have interior nodes for if the order is more than linear. So, we can have a tensor family which is more widely used, which is called serendipity family, in which nodes are only along the boundaries of the element. And let us try to define 1 or 2, let us say we will restrict to linear and quadratic. So, linear one is very simple, it is a 8 node element which is also referred to as simple brick. One, two, three, 4, 2, 3, 4, we have got 5, 6, 7 and 8. So, this is our 8 node element, 8 node linear element. Now, for this 8 node linear element, the shape functions are identical to what we will get for linear Lagrangian element, and we have got all corner nodes. So, a shape function is given as n a is equal to 1 by 8 into 1 plus xi a xi into 1 plus eta a into eta times 1 plus zeta a times zeta, where xi a, eta a, zeta a, these are coordinates of node numbered a. So, by substituting the appropriate values, we can find out the shape function for each, or shape function corresponding to each node for this 8 node linear element. Next, let us have a look at a quadratic serendipity element. So, let us first draw a small diagram. As usual, we would number these nodes starting in a specific order. So, 1, 2, 3 and 4, there are 4 corner nodes in the bottom plane, and 5, 6, 7, 8, these are corner nodes on the top plane. So, we are dealing with the case this quadratic 20 node element. Okay, now how do we define the mid nodes? Their numbering now will start in order. Let us say one midpoint of 1 and 2, this will be numbered as 9. So, 9 go in the same fashion, 2, 3, that gives us the node number 10, 3, 4 midpoint, that gives us 11, 4 and 1, 12. And next we will have a look at the vertical things. So, 13, 14, 15 and 16, and after that we will have these top midpoints, the top sides, 17, 18, 19 and 20. So, in 3 dimensions you quickly say that if you move from linear to quadratic, the number of nodes has increased considerably. In fact, if we had a Lagrangian family, we will have a much larger element of nodes. There will be many more nodes in the interior. There were 7 more nodes to be precise. Now, how do we represent our shape functions in this case? So, shape functions for corner nodes, you can just remember the way we did it for 2D case. So, n a is 1 by 8 1 plus xi a into xi 1 plus eta a into eta 1 plus zeta a into zeta multiplied by xi a xi plus eta a eta plus zeta a zeta minus 2. So, this is a very compact form expression for our corner nodes. Substitute their natural coordinates xi a, eta a and zeta a to get the corresponding shape functions. Now, let us have a look at what would be the form for midpoint nodes. So, let us take one typical case, remaining ones you can work out yourself. So, typical midpoint node for which your xi a is equal to 0 and eta a can take value plus or minus 1. Similarly, zeta a takes the value plus minus 1. Your n a is expressed as 1 by 4 1 minus x psi square into 1 plus eta a eta into 1 plus zeta a zeta and so on. So, similar expressions can be obtained for other set of midpoint nodes. So, what we have done is just identify one set for which, let us say, this eta a coordinate set to 0. So, the first term was in terms of 1 minus xi was set to 0. So, first term was 1 minus xi square, remaining terms very similar to what we had, that was the product of 2 linear terms in eta and zeta. So, if you move on to the case of eta a is equal to 0, then the shape functions would involve the linear combination in terms of xi and zeta multiplied by 1 minus eta square and so on. So, that is how you can easily write down the expressions for the remaining shape functions, and now that I would leave as an exercise for you to complete. Tetrahedral elements, I said that is a reading assignment for you. And then what we use the word isoparametric element, specifically when we discussed our triangular element, we said look, it also works out to be linear triangle is an isoparametric element. So, what do you mean by an isoparametric element in general? The definition is the elements for which shape functions can be used to represent the geometry as well as the function approximation, they are called isoparametric elements. So, that is to say, if you got any element for which shape functions are represented as ni, so isoparametric elements. So, shape functions they are given by ni, let us say I is equal to 1 to the number of nodes in this element. Then the geometry can also be expressed using NIs and nodal coordinates. That is, we can write x as sigma Ni xi, y would be given as sigma Ni yi, and z would be represented in terms of sigma Ni zi. So, if that were the case, such elements are called isoparametric element. Iso means identical or same. So, here the variation of the variable in our element and variation of the coordinates, they follow the same pattern, they follow similar pattern, they are related by these shape functions. So, that is the reason why we call such elements as isoparametric elements. Now, let us come to the evaluation of integrals. Now, for most of the finite elements, analytical integration would be very difficult, if not impossible. So, we have got to go for what we call numerical integration. There are separate set of formulae which are available for rectangular elements and triangular elements. So, if you are dealing with the 1 dimensions or in 2D rectangular or 3D brick elements, so we would use Gaussian quadrature formula. So, Gauss quadrature would be used for 1 dimensional elements as well as multi-dimensional rectangular elements. So, let us have a look at what we mean by the Gaussian quadrature here. Just to remind you that if you want to integrate a function f x we have got a function which has to be integrated along a line, and suppose the extent of this line, let us call it as Lx, let us say it is a to b. So, we want to find out this integral a to b fx dx. Now, you can verify that this is given by Lx by 2 if we map it to an isoparametric element with the extent -1 to 1, so x and the natural coordinate xi which ranges from -1 to 1. So, in this we can write it as -1 to 1 f x of xi dxi, and Gauss formula says that now this standard integral in the interval -1 to 1 f xi dxi, it can be obtained by this sum, weighted sum I is equal to 1 to n g f xi wi. So, here there is xi points, they are called Gauss quadrature points, and wi are called weights. Okay. So, we can use this Gaussian quadrature even for multi-dimensional integrals. For instance, if you want to find out an integral in 3 dimensions, that is to say we want to find out the integral given by integral over 3 dimensional domain g x d omega. So, this we can easily express as minus 1 to 1 minus 1 to 1 minus 1 to 1 g x. Now, x would be given in terms of x I eta zeta multiplied by what we call a Jacobian dxi d eta d zeta. And now, this is standard integral minus 1 to 1 minus 1 to 1 minus 1 to 1 g times dxi d eta d zeta can be obtained using Gaussian quadrature formula. Let us say I is equal to 1 to n 1 sigma j is equal to 1 to n 2 sigma k is equal to 1 to n 3. Let us call this function as a g bar xi I eta j zeta k multiplied by the weights. So, multiplied by the weights w I, w j, w k, wherever g bar xi eta zeta, this is our function g multiplied by Jacobian. So, this is how we can use Gaussian quadrature to find out 1D or multidimensional integrals numerically. Next, we have got some special quadrature formula for triangular elements. For triangular elements, we already see that there is one possibility of doing some analytical integration, and there is a special formula which is fairly similar to what we had seen with the Gaussian quadrature. That is to say, we will have some Gaussian points and their corresponding weights, which can be used to find out the integrals over an area element. So, now let us have a look at the integral over a triangular element. Now, if everything is in terms of the area coordinates, we have got one simple relation which we can make use of in the evaluation of these integrals. So, there is one analytical formula. So, integration over a triangle, we got L1 time to the power a, L2 to the power b, L3 to the power c d omega. This is given as factorial a, factorial b, factorial c divided by a plus b plus c plus 2 factorial multiplied by 2 into the area of the triangle. So, this is one analytical formula. Now, let us have a look at numerical formula similar to the Gaussian quadrature. So, numerical integration. If you want to find out the integral which is given by integration over the area of some function f x d omega, this we can write as 2a integral over 0 to 1 integral 0 to 1 minus L1 f L1 L2 L3 d L1 d L2. Remember that we have not introduced L3 because that is not an independent coordinate, that is given in terms of L1 and L2. So, now this is standard integral which we get here. For that there are specialized formulas. So, this integral, let us call this as I1. So, integral I1 is equal to 0 to 1, 0 to 1 minus L1 f of L1 comma L2 comma L3 d L1 d L2 this can be expressed in a form very similar to our Gaussian quadrature, that sigma I is equal to 1 to n f at L1I, L2I, L3I times weight Wi. So, there are standard tables available. Say for instance, if you want, I will just put two possibilities here. In one case, we have got a single point formula. Okay. So, single point, the coordinates of this point, let us call this point as small a. So, coordinates are 1 by 3, 1 by 3, 1 by 3, and the weight W1, this, as you can easily guess, this would be equal weight. So, the weight is 1. Similarly, if you want to have, so this gives us first order accuracy. If you want a quadratic formula, so that will involve use of 3 points which are basically midpoints of the sides, okay, and the coordinates you can easily say this is 1 by 2, 1 by 2, 0. In fact, let me call this as A1, A2 and A3, 0, half, 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 0, half. So, this is 3 point formula. Weights are again equal. So, W1 is equal to W2 is equal to W3, 1 by 3. So, use these coordinates in this formula which we had used. So, the summation would be over these 3 points using the function evaluation at the points A1, A2 and A3, and weight multiplier is 1 by 3, and this should give us the numerical value of the integral. Now, to conclude our numerical integration, there are certain points which I would like to just point out. The required order of numerical integration, because more number of points we choose in Gaussian quadrature or this for triangular elements or similar formulas are available for tetrahedral elements, more expensive would be evaluation of the integrals. But do we really need that? There are some simple rules which say no, we can restrict the number of points which we need. So, the total number or total degree to which we need to evaluate our integrals exactly is 2p minus 1, where p is the degree of polynomial present in our shape functions, that is whether we have used linear, quadratic and so on shape functions, and m is the order of differential present in our weak form. So, if m is equal to 1, so if you want to use linear elements, we should restrict p to, we should use only first order formula. For instance, in the case of triangular elements, just taking the value at the centroid, that should be good enough, use 1 point formula. If you are using quadratic element, use p is equal to 2, for quadratic elements use a quadratic formula, or in the Gaussian quadrature use 2 by 2 formula. So, thus for a linear quadrilateral triangle, a single point integration is adequate, and for a quadratic element, let us say if you are dealing with rectangular one, we can choose 2 cross 2, that is 4 Gauss points in 2 dimensions, and 2 cross 2 cross 2, that is 8 points in 3 dimensions to obtain our value of the elemental integrals. We do not need anything more than that. Same would be the case if you want to use triangular elements, use 3 points in 2D, and there are similar extension in 3D with the tetrahedral elements. For further details on these procedures, please have a look at the book by Chung on computational fluid dynamics, FEM section, or Reddy's book on Introduction to Finite Element, or the most definitive book of them all, Jinkwitz, Taylor and Zhu's book on finite element method, its basis and fundamentals. So, we are not going to discuss any further about these shape functions, we are going to put a stop here. In the next lecture, we will see application of finite element method to heat conduction problem.